So in section 8.5, we have a look at heat in chemical reactions, and this is a very important topic. Chemical reactions always involve a change in energy, and sometimes heat is taken in and sometimes heat is released. And a classic example of a reaction that releases heat is respiration. So when we breathe, and we convert our food into carbon dioxide, ultimately, respiration occurs and that reaction generates heat, which helps us maintain homeostasis. Now, if that process isn't working too well, we can either become hypothermic or hyperthermic. So if we get exposed to an external source of heat, our temperature might rise and we get sick pretty quickly. We can get heat stroke and other things. And if we get cold, we have similar issues because our temperature of our body needs to be maintained at a very specific level in order for all of our biological functions to work well. Now, physical and chemical changes are always accompanied by the transfer of energy. So when an ice cube melts, the reason that it's melting is because heat is going into the ice cube. When a fuel burns, remember we said combustion is always accompanied by the release of heat and light. When an explosion occurs, what's happening is that we're having a decomposition reaction that results in the formation of a gas, but also a lot of energy. And so that gas expands rapidly. So chemical processes can be classified as being either exothermic or endothermic, depending on whether they take in or give out thermal energy or heat. And thermal energy is just another term for heat. So a reaction is described as being exothermic if it gives out thermal energy. So that example of respiration is exothermic. A reaction is described as being endothermic if it takes in thermal energy. So endothermic reactions can be recognized because they'll suck heat from the environment, making the environment colder, which is kind of interesting. Exothermic reactions can be recognized because they release heat out into the environment, making the environment warmer, which we can sense. So a good way of kind of getting used to these labels, exothermic and endothermic, is by considering the familiar changes of state. So if I want to go from a solid to a liquid, we call that melting. And it's not surprising that I have to put heat in to make that happen. And that is an endothermic process. So remember that entrance, right, means to go in, doesn't it? Right? Make an entrance means to go in, right? So endothermic means heat going in. If I want to go from a liquid to a gas, well, if I want to evaporate some water, I'm going to put a pot of water on the stove, aren't I? I have to put heat in, okay? So evaporation is an endothermic process. So when I want to go the other way, then I'm going to get the opposite change in heat. So when I go from a gas to a liquid, when condensation occurs, heat will be released. This is an exothermic process. So you probably heard that steam causes particularly nasty burns, and one of the reasons is because when it condenses on your skin, it releases some heat. When a liquid goes to a solid, that is when it freezes, heat is released. Heat is taken out or flows out of our sample of matter when that occurs. All right. So you can see if a process is endothermic in one direction, then it is exothermic in the other. Now there are two changes of state that are less well known, but are pretty well known in chemistry. One is when a solid goes directly to a gas without going through the liquid phase. That's called sublimation, and that is an endothermic process. And so a good example of this is carbon dioxide is a solid at low temperatures, and it goes directly to a gas without going through a liquid state. So carbon dioxide solid is referred to as dry ice because you can pack something in solid carbon dioxide to keep it cold, and the ice doesn't turn into, liquid, it just goes directly to the gas, so your material doesn't end up getting, soaking wet. And so we use this when we're like packing items for shipping to stop the item from getting wet. Now, if a gas goes directly to a solid without going through a liquid, we call that a deposition, and that process is exothermic. So that means that it releases heat when that occurs. There's a few examples of this that are pretty common. One of them is on really cold days, you can kind of get like hoarfrost, where it seems like water vapor just freezes out of the air, it goes directly to being a solid without going through the liquid phase. But probably a kind of a common one that's well known is like, well, not well known for everybody, but if you've ever been to a volcano, you might see sulfur solidifying directly undergoing deposition. What happens is it just goes directly from the gas, it's kind of a yellowish gas, to a yellow solid without going through the liquid. Okay, so this is the important thing, and I mentioned this previously, that a process that is exothermic in one direction will be endothermic in the other. So if a reaction is flipped, you know that the change in energy is going to be different. So if I want to go from solid water to liquid water, well, that's, melting ice. I have to put heat in to make that happen, right? Now, I automatically know because of that observation that if I want to go from liquid water to solid water, I have to take heat out. All right, so that's, heat will be a product of that reaction. So that's what we're talking about here. When you change the direction of the reaction, you change the direction of the heat flow. Okay, so we'll often indicate the changes in energy in a chemical reaction as we move from reactants to products, and using what we call an energy diagram. So in an energy diagram, what you have is reactants written on the left and products written on the right. And so the x-axis is what we call the reaction progress. We're moving from reactants to products. And then on the y-axis, we have the energy changes that are occurring. And you can see in this case, the products lie higher in energy than the reactants. So that means that energy was absorbed, and this must be an endothermic process. Now, in this case, you can see that the products are lying at lower energy than the reactants. So that means that energy was lost. So this must be an exothermic reaction, and I would be able to recognize that because I would be outside the reaction. I would feel heat radiating from it. In this case, I would feel cold because this reaction would be sucking heat from the environment into the reaction. Now you can see here that we've drawn a curve with a hump in it between the reactants and the products. So what the heck is that all about? Well, it turns out that for any chemical reaction to begin, to get going, the reactants have to have enough energy to overcome this little barrier that we call the activation energy, and that's what we're indicating here. And you've probably noticed this, if you mix like gas and oxygen together, it doesn't immediately react, but you put a tiny little bit of energy in, you put a spark in there, and poof, it'll start burning, and then it'll just keep going spontaneously without any, once you give it that little nudge to get it going. So that little nudge that it takes to get it going is referred to as the activation energy. And, you've probably noticed this with just, tasks yourself, felt this. It's like, there's like a lack of inertia to get beginning. And then once you start the task, it kind of keeps going spontaneously. That's the activation energy. All right. So for every reaction, there's always this little barrier that it has to get over before it can kind of get moving, if you will. All right. So problems in ALEKS involve interpreting these energy diagrams. So here's a hypothetical chemical reaction. All chemists love this one. A plus B gives C and D. And it doesn't really matter what the reactants and products are here, other than that the products are different from the reactants. So here's our energy diagram. We know that the reactants are written on the left and the products are written on the right. And in this case, the products are a lot lower in energy than the reactants, so heat is released, right? So this is exothermic. Exit means to leave, right? Just like entrance means to enter, make an entrance. So what is the heat of this reaction? So we have to look at the scale here carefully. So we started at 250 and we went down to 50. So what happened was that there was a loss of 200 kilojoules, and the units there are kilojoules per mole. Now how we indicate this, it says what is the heat of reaction. Heat of reaction means the change in the heat, and so in this case it was minus 200 kilojoules, right? Minus 200 kilojoules. So then it asks, is the reaction exothermic or endothermic? Well, heat is lost, so it was exothermic. And then we're asked, can we determine the activation energy? And we can. The activation energy is the difference in the energy between the reactants and the peak of this little hump here. So we started at 250 and it goes up to 400 right there. So we had to put in 150 kilojoules per mole to get it going. So we're going to go yes, and it is 150 kilojoules per mole. And then it says, could you determine the activation energy of the reverse reaction? Well, that would be from there to there, wouldn't it? So that would be from 50 all the way up to 400, which is a change of 350. So yes, 350. And that explains why this reaction doesn't run backwards, right? Once it goes over here, it gets stuck down here because it would have to overcome such a huge barrier to run backwards. So this reaction just runs only in the one direction, unless there was a lot of energy around that allowed the products to overcome the activation barrier for the reverse reaction. Okay, so that concludes this short section on heat in chemical reactions, and that's all we're going to be doing for this chapter. So let me know if you have any issues and I'll be happy to help you out.